Fusion Mobile, quality e-learning experience on the go.
Welcome to Fusion Mobile e-learning clinic. I'm Sanyaola Olua and I will be walking you through the physics course. We'll be talking about the Newton's law of motion, and in this topic we'll be looking at the dynamics. We'll talk about Newton's first law of motion, we'll look at Newton's second law of motion, and Newton's third law of motion. Alright, let's start. What is dynamics? Well, before now we talked about motion, and we looked at the basic formulas that are used in motion. We talked about velocity, acceleration, and all the other things as that. But we never really considered the things that cause motion. Well, when we are considering motion in itself, on its own, we're talking about kinematics. But when we consider motion in relations with those things that bring about motion, those things that cause those changes, that bring those things that induce the motion, we're talking of dynamics. That's the area of dynamics. Well, the major thing that is responsible for motion, which is as in for changes in motion, that is either the stopping of a body or the movement of a body from rest, is force. Yes, force. Force is any push or pull, any action that alters the current state of a body. Now, force can be in two forms. We have the forces that we call the contact forces, and we have the forces we call the field forces. We have the contact forces and the field forces. A contact force is a force that must make physical contact, must touch the body for it to be of any effect on it. For example, a push or a pull. When you pull a thread or you pull a wire, the force that is being used up there is a contact force. So we can call forces like tension, like pressure, like tension, like upthrust. Those are contact forces. While we also have field forces. Field forces are forces that act on the body within the field. A field is a region in which a particular force is acting. Now, these forces do not need to make contacts with the body to affect it, but rather when the body finds itself within their axis, within their area, they experience the presence of these forces. Such forces as gravitational force, as magnetic force, electric force. All these forces exist within the fields which all these forces exist within the fields in which they do operate. I haven't spoken about forces and dynamics. Some questions will pop up on your screen in a few seconds. Please attempt them. We want to see how much you've understood what has been taught. Newton's first law of motion. So Newton propounded 3 laws of motion, and in his first law he said that a body would remain in a state of constant rest or in constant motion unless an external force is applied. Now, this suggests that if there is a body, let's say a ball rolling, it will continue to roll till infinity. And if the ball was stationary, it will continue to remain at its spot unless an external force comes to act on it. This law is very true. This law is very true, and it has been applied especially in the area of momentum. What is momentum? The momentum possessed by a body is calculated as the mass of the body multiplied by the velocity which the body possesses. So that's momentum, capital M, equals mass multiplied by velocity. So should there be a body and the body possesses no momentum? For a body to possess no momentum, it means it has no velocity, it has no speed. So, but if there is another body that possesses momentum, it can keep moving. Momentum is supposed to be an inertial. It's supposed to be something inborn inside a body, and it's not supposed to be something that can be taken out. Of course, according to the law of conservation of energy, energy is neither created nor destroyed. So these are the guiding principles that bind us in our work with momentum. So peradventure, we have two bodies that are moving, body 1 and body 2. Body 1 has a mass of m1 and a velocity of v1. Body 2 having a mass of m2 and a velocity of v2. Should they be moving in the same direction? Of course, direction matters when we talk about vector quantities. We know velocity is a vector quantity. So momentum also is a vector quantity. Now, should they be moving in the same direction? If they should collide and move together, there are several conditions that could happen. There are about 3 different conditions that could happen. They can collide, stick together, and move together in one direction. They can collide and one of them would move while the other stays stationary. And they can collide and both of them move in opposite direction. So whatever would happen, what should be noted is momentum before, let me use U for initial velocity and V for final velocity. So U1 and U2, and they will have V1 and V2. So momentum before collision, the total momentum before collision must be equal to total momentum after collision. That's one of the things that Newton's first law suggests. So it's a body would remain in a state of rest or constant motion unless an external body comes to make contact with it. Newton's second law of motion. Newton's second law of motion states that the rate of change of momentum is directly proportional to the force applied. We said earlier, the first law of motion says that a body will remain unless an external force acts. Now, when an external force acts, the rate of change is directly proportional to the force applied. It's stating that, in other words, that if the force is F, the rate of change of momentum, of course, the mass will remain the same, while velocity will change from from U to V. So it says the rate of change. Of course, when you put rates of change, we usually consider time. And of course, if we can put it as F equals m VU m into bracket V minus U T. And we should remember acceleration is V minus U. Our acceleration is V minus U. Our acceleration is V minus U. V is the final velocity, while U is the initial velocity. So the difference, of course, we know acceleration is the rate of change of velocity with time. The time rate of change of velocity. So that is our acceleration. So that's how the formula F equals to ma was developed. And how do we see the application of Newton's second law? Newton's second law has a couple of applications. You see, it should also be borne in mind that acceleration is also a vector quantity, which means acceleration, whether it would increase or not, is sensitive to direction in which it occurs. Let's take into consideration a lift, an elevator. A man in an elevator, his weight changes in the course of movement of the elevator. While the elevator is going up, his weight increases. I know you might be wondering, how come? Why would his weight increase when the elevator is going up? But let's see how it works. When the elevator is going up, it means the body is having an acceleration. Using the knowledge of relative motion, it means the body is having an acceleration right now at that particular time, and a particular force is going to be needed to drag that body up. So that force that will be needed at that particular time equals to MA. I believe you agree with me on this. Now, putting aside our relative motion, in actual sense, there is already a force on the man, and that is a pull of gravity, gravitational force, which is dragging him down. Now, for this body to be able to move at this particular A, this A that we measured, assuming that there is no gravitational force, the gravity is acting G. Now, for the body to actually be able to move at this particular A that we are indicating that it wants to move at, then we must also put into consideration this G. This G must be overcome by an extra measure of A, which means the total amount of force that will be needed to drag the man up would be MA plus mg. So the total force required, which if we place a weighing balance beneath the man, the weight that the man will be having at that particular time would be m into brackets A plus G. And we know that the original weight of the man is mg. So his weight actually increases. But when the elevator is coming down, his weight reduces. His weight reduces. In fact, he might get to the point of being weightless. Should the elevator come down with an acceleration as high as that of gravity, it would mean the acceleration of gravity would be cancelled, and the man, if he should come down with a velocity as high as that or less, the man might actually start floating inside the elevator due to the situation of weightlessness that has been temporarily created. So, in this particular condition, we'll be having, let's take it one after the other, the way we did for the first one. The first thing would be, we want to assume there is no weight, as in there is no force of gravity acting. So it wants to move down with a particular acceleration, and that acceleration is A. So the force required to move down, of course, that's going to be a negative force. Since it's not moving up, we don't need to drag him, we can just easily let go. So that's the force with which it will drop. It's a negative force, that's MA. And there is already the force that is dragging the man down. So that's mg, because we cannot cancel out gravity. We cannot ignore gravity. So gravity now is acting downward. So at that particular point in time, the force that is required for us, otherwise, gravity naturally is the one creating the downfall. It is gravity that is pulling the elevator down, because everything that goes up naturally wants to come down. So for us not to fly down at the acceleration of gravity, we need to have a certain amount of tension on the tension wires of the elevator, is what we are trying to calculate now. So of course, we would like to have our positive value in front and our negative value behind. So we have mg minus ma. We want to come down at this particular velocity. So it is in opposition to the natural flow of the elevator. The elevator is coming down. The force that will be required, because the tension wire is always at the top, is always holding it at the top part. The force that will be required to be possessed by the tension wire will be determined by, be calculated by M equals G minus A. And actually, if you place a weighing balance beneath the man while in the elevator, his weight will be reflecting this. That's why when we are going up in an elevator, you feel like a kind of pressure is on you. And when you are coming down in an elevator, you feel like you are lighter. You feel less in your weight. Newton's third law of motion. Newton's third law of motion states that to every action, there is an equal and opposite reaction. Very beautiful law. I like it. Let me give you an instance. I'm angry. I'm very, very angry. But I want you to exert that anger on my behalf. On my behalf, hold your hand in a fist and around your pen and tighten it. Now, if you'd observe, as you are forcing your hand around your pen starts to force itself against your hand, thereby creating pain. The pain may not be that much, but that's because that's about the much of pain you are inflicting on the pen. If you should hit the wall with a small punch, you feel the pain, you feel the touch. But if you should decide to increase the force and make it larger, you feel the force as well. Even though you might succeed in breaking the wall with your punch, but you would actually feel the pain. So, to your action, there is a reaction from whatever thing you're exerting your action on. So that's the law, that's Newton's third law. And there's also the Newton's third law of motion also supports the law of conservation of momentum. Putting all the laws of Newton together, you see the law of conservation of momentum come into play. A body possesses momentum. Now, momentum is neither created nor destroyed, just like it is said about energy. That's Newton's law. That's law of conservation of momentum. So momentum is never created nor destroyed. It's only being transmitted. That is total amount of momentum before collision. That is when we have two bodies now. Total amount of momentum remains constant all through. And that's why we have the formula. And in most of our works, we'll be working with bodies hitting themselves and sticking together and moving with one velocity. So what we usually work with in physics, especially at this level, is we'll say momentum of the first body, that's m1 u1, plus momentum of the second body, which is m2 u2, would produce the sum of the masses of the bodies, m1 plus m2, multiplied by the joint velocity with which the bodies move when they stick together, v. Momentum of the first body, m1 u1, plus the momentum of the second body, m2 u2, equals the joint mass of the bodies, m1 plus m2, multiplied by the uniform joint velocity with which the two bodies move, v. So when we have two bodies initially, this one is m1, it possesses u1, it's coming, and this one is also here, it's m2 and u2. They collide. So after they collide, and after they collide, they stick together and move together with one velocity, m1 plus m2 moving with v. So that is what Newton's third law of motion states. Now, I want you to always keep in mind, every time you're working with vector quantities, directions matter. Directions matter. If these two bodies are moving in opposite directions, if this one is positive, if you're taking forward direction as positive, then backward direction should be taken as negative. If you're taking backward direction as positive, then forward direction should be taken as negative. In a case where we have two bodies, M1 and U1, M2 and U2, this one is coming like this while the other one is going the opposite direction, and they join together and move in one direction. What our equation would look like would be M1 U1 minus M2 U2 equal M1 plus M2 V. So even though, yes, this is the ultimate formula, mass does not have direction. That's why whenever they stick together, they share, and if they do not stick together, they have each of them will have its own individual it will have its individual mass and velocity. But at this level, we'll be working with the ones that stick together and move together. So bear in mind, if they are in opposite directions, they have minus. If they are moving in the same direction, they have plus. Let's take this question. A body of mass 20 kilograms moving with a velocity of 3 meters per second collides with I think that's another body. Another body of mass 10 kilograms moving at 10 meters per second in the opposite direction. If they stick together and move, what would be their joint velocity? The joint velocity. Alright, let's look at our parameters. The first body, let it be the ones, that's M1. It has a mass of 20 kilograms. 20 kilograms and a velocity U1 of 3 meters per second. The second body, M2, is 10 kilograms and velocity U2 is 2 meters per second. So, well, we are told that they stick together and they move with a joint velocity, which we don't know. So from our formula, M1 U1, they said they were moving in opposite direction, so we know it will be minus M2 U2 would be equal to M1 plus U1 and plus M2 V. That's our formula. So substituting our parameters in, 20 multiplied by 3 rather, minus 10 multiplied by 2 equals to 20 plus 10 V. This is 60 minus this is 20 equals to 30 V. 60 minus 20 gives 40, G equals 30 V. So our V will be equal to 40 over 3 over 30, which equals 1.33 meters per second. In this topic, where we looked at the Newton's laws of motion, we described dynamics as the study of motion and the things causing the motion. We discussed the Newton's first law of motion, which states that a body would remain in a state of rest or constant motion unless an external force is applied to it. And we said the second law of motion says that the rate of change of momentum, the time rate of change of momentum, is directly proportional to the force applied. The third law of Newton's third law states that to every action there is an equal and opposite reaction, and this led to us considering the law of conservation of momentum, which tells us that the sum of the momentum, the total momentum of a system, is the same at every point in time. To see applications of the laws of Newton's are numerous. We see it a lot in almost everything we do in our day-to-day lives. I gave an illustration of you gripping your pen, or I advise you to punch the wall. We can also see further applications of Newton's laws in the ejection of rockets. Space explorations have really depended on Newton's laws of motion. And also the recoil from a gun. When you shoot a gun, I know many of you can't shoot guns because if you shoot one, it will throw you away, actually. Yes. With the same force with which the bullet comes out of the gun, a force of that magnitude is used to push the shooter backward. In a few seconds, some questions will pop up on your screen. Please do well by attempting them. And you can view the video over again if there is anything you think you might have missed out.